There are essentially two routes to discovering quantum field theory. The first thing you do is you take a classical field theory, like say electromagnetism, and you quantize it. And if you do that, you find that you get particle-like excitations of the field. The other way to go is to take the quantum theory of a particle and then generalize it to many particles. And if you do that, you find that you end up with exactly the same mathematical structure that you get for quantum field theory done the other way. And perhaps unsurprisingly, therefore, there are approximations where the quantum theory of large numbers of particles can also behave like classical fields. In other words, quantum field theory is the deeper, correct theory of the universe. And if you look at it in a particular way and squint, you tend to see classical fields. And if you look at it in a different way and squint, you tend to see particles. And depending on which of those things we saw first, so for electromagnetism we first saw the classical fields, and so we tend to think of those as fields that we quantize to discover photons. Whereas, say, electrons, we first discovered electrons, and so we tend to think of quantum fields of electrons as lots of particles stuck together. But in fact, mathematically, those two very different descriptions are actually extremely similar under the hood, and we could have derived either from either direction. Now we're going to take the second approach where we get the quantum theory of many particles at once, and indeed we've already started down that road because we know that if we have a single particle, the state, which is going to be the element of some Hilbert space for that particle, can be written out in terms of the basis states of that Hilbert space. And if we have n of those particles, then the state is just going to be an element of the tensor product of all those Hilbert spaces, and we're going to need a complex number for every possible combination of basis states. So it's a very large Hilbert space. Now there's really only a single piece of physics missing, and that's a very simple but very powerful principle. It's called the principle of indistinguishability. And what that says basically is that any two fundamental particles of the same kind are absolutely identical in every sense. In other words, the universe cannot distinguish between them. So if I was to take one electron from my brain and one electron from your brain and swap them, provided I swapped the state that each of them was in precisely, everything would work exactly the same way. Okay, so if everything has to work exactly the same way, let's have a look at this wave function here. This is our state, and these coefficients contain all the possible information that describes that state. So these are just the basis states here, and these are the coefficients. So if we swap two of those particles, the principle of indistinguishability says that any experiment we do on that resulting state must give us exactly the same results as any experiment we do on this state. Now what consequences does that have for the coefficients?